Notice a couple of you just came in. So we're talking about, in this book, it's, section 4.4, it's called counting. It's not necessarily regarding how to count, but it tells you or deals with how to determine a total amount of some situation. So you're still doing probability, and let's say that you don't have the total sample space or the total amount of some situation. This is, there are a few rules here that we're going to talk about that deals with that, how to calculate the total amount of. So the first rule that we're looking at is called the fundamental counting rule, which is now also called the multiplication counting rule, which says this: for a sequence of events in which the first event can occur this many ways, the second event can occur that many ways, the third event can occur another amount of ways, and so on, the total number of outcomes is the product, which is why it's called the multiplication counting rule. Like I said, a lot of times I read this to my students, they don't know what the heck I'm talking about. So here's an example dealing with that. What is the probability that you randomly select my social security number? Now the book, they usually talk about, like I said, the president's a social security number consists of 9 digits in a particular order, and repetitions of digits is allowed. After seeing the last 4 digits, if you randomly select all the digits in the social security number, there are 9, what is the probability of getting the social security number of the president? Well, I'm going to say mine because politics right now is too crazy. So you're randomly generating 9 digits to represent a social security number. Each digit can be repeated. Repetition is allowed. That matters. What is the probability of getting my social security number? So, before you could deal with that, you have to deal with how many total possible there are, because only one of them is mine. How many total possible social security numbers are there? So what I like to do with this kind of situation is, okay, so there are 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 total digits in a social. Each digit is a single digit number. How many ways or how many options do I have for the first single digit number? Well, how many single digit numbers are there? 10. 10. There's 10 because we're including 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 total, right? Single digit numbers. So I have 10 options, right? 10 different ways that I could select the first digit. I'm allowed to repeat the digit, right? So how many ways can I select the second digit? Again, it's a single digit number. It could be the same as the first. How many ways can I select the second one? Well, there are still 10 different single digit numbers that I could pick from. How about the third? I could repeat those numbers. So again, there's 10 total possible, single digit numbers I can choose to put in that location. And then 10 for this, and 10 for this, and 10 for this, and 10 for this, right? Because I can repeat my digits. So the fundamental counting rule or the multiplication counting rule says that I have this many ways to do this many ways to do this many ways to do this. Multiply all of that out and you'll get the total amount of ways that you can actually select 9 digits where you could repeat the digits, and there's 10 options per single digit. I'm not even going to 10 to the 9th power, right? Or 1 with 9 zeros. 10 to the 9th power. So there's 10 to the 9 total types of social security numbers out there. Now you're randomly selecting one of them. What is the probability that you get my social security number? Well, there's only one that is mine out of a total 10 to the 9th. This is the probability. I'm not going to put it in decimal form because it's going to be really small. Okay. Now, let me add to that. What if you know the first 4 digits? You know the first 4 digits of my social. Now, you only have to guess on the last 5. There's still a total of 9, but you know the first 4. You don't have to guess there. Those are known. You just have to guess for the last 5. Now, what's the probability that you select or randomly generate my social security number if you know the first 4 digits? Well, I still have 10 options for this digit, the 5th digit. I still have 10 options for the 6th, and 10, and 10, and 10. But 10 times 10 times 10 times 5 times is 10 to the 5th power. Now, obviously, there are less possible outcomes because I know the first 4 digits. Now I only have to guess the last 5. So 10 to the 5th types of ways that that can happen. Only one out of that is mine. So the probability of randomly generating my social security number, if I know the first four, or you know the first four because you're guessing mine, if you know the first 4 digits, you're randomly generating the last 5. 1 out of 10 to the 5th power. Okay, 10 to the 5th. I know that looks funky. That's 10 to the 5th power. Okay. One more example using this rule. And I'm going to type this because I don't want to write all this out. This is kind of my own little example. So, a case that is locked. Okay. Remember, I'm not an English professor, okay? A case that is locked with a code has $1 million in it. You have to randomly generate the code because you're trying to get that $1 million. What is the probability that you randomly, you're only trying once, you get one shot. What is the probability that you randomly generate the correct code and get your $1 million? The code has the following. The first 3 digits are letters of the English alphabet. And the last 2 digits are single-digit numbers. The letters can be repeated, but the numbers cannot. Boom. It's $1 million, you know. You got to work for it. So you have a case that has this code, and it has 5 total, digits, right? 3 initially. Let me just make 3 initially, and then 2 after that. And the 3 initial digits are letters of the alphabet, and then the last 2 digits are numbers. Now these letters, can the letters be repeated? The letters can be repeated. I'm just going to put a check mark, okay? The letters can be repeated, but the numbers cannot. That's what I mean by that. Numbers cannot be repeated, letters can. What is the probability that you get one shot and you randomly generate this proper code? What is the probability that you get your money with one shot? Okay, one chance. One chance. Well, obviously, I need to determine how many total codes there are because only one is the correct one. 1 out of I don't know how many. So I have to determine the total sample space, the total amount of outcomes, right? That's where this rule is going to come into play. Well, let's start this off. My first digit is a letter of the alphabet. How many options do I have for that? Anybody can answer. How many options? 26 letters of the alphabet, our alphabet, right? 26 letters of alphabet. Now, I'm allowed to repeat that. So for the second digit, which is another letter, which could be the same as the first, I still have 26 possible outcomes. I'm allowed to repeat the letter and do it a 3rd time. So again, 26 possible outcomes. But now I go here, I have to pick from numbers, single-digit numbers. And again, we said already that I only have 10 possible single-digit numbers that can go here. But I am not allowed to repeat it. Therefore, how many do I have to choose from here once I place a number here? I only have 9 options. Good. The multiplication counting rule says if I multiply all these different cases, right? I have this many ways to do this many ways to do this many ways to do this, blah, blah, blah. Multiply it all out, I'm going to get the total amount of ways that I could do it all together, also known as the total sample space, the total amount of codes that are possible given those conditions. 26 times 26 times 26, oops, times 90, which is this number here that I'm just going to write down real quick, 1, 581,840. I'm missing digits. 1,581,840. So only one of those is the correct code. You got one out of 1,581,840 chance to actually generate the proper code. You got one chance to go get your $1 million. Let me see what that is in decimal form. That is, and I want you to see this too, one out of that. When you guys do your calculator, I want you to notice that you have the 6.32 blah, blah, blah. Don't forget this E -7. So you're going to see this now, especially when we get to probability and things like that, right? This is scientific notation. Your calculator uses this E to indicate scientific notation. So this means 6.321 blah times 10 to the -7. That means I'm going to take this decimal and move it to the left 7 places. To the left 7 places. So what did I say it was? 6.322. Let's just go 6.32. 6.32 times 10 to the -7. 0.1, 2, 3, 4, 5, 6, 7. Right? I'm not even going to put that in percentage form. Obviously, it's a very low percentage. Obviously, it's unlikely, which would make sense, right? Because you got one shot to do this. It's $1 million. I mean, I'm not, I'm not dealing with prayers and luck and all that. This is just, statistically speaking, okay? So this is what we call the multiplication counting rule or the fundamental counting rule to determine the total number of outcomes under these kind of conditions. So that's my first rule.